Adam Riess, Nobel Prize in Physics 2011, Johns Hopkins University. His exact words were, "We have misunderstood the universe." He did not say this as speculation. He said it after his own data came back from James Webb. He measures how fast the cosmos is expanding. The number he measures does not match what our best model of the universe predicts. If he is right, every timeline in cosmology, the age of the universe, the first stars, and the conditions for life are wrong. The Planck satellite spent 4 years measuring the afterglow of the Big Bang. That afterglow, the cosmic microwave background, is a faint pattern of temperature ripples stretched across the sky. Each ripple encodes how sound waves moved through the early universe, when everything was still a dense, hot plasma. By analyzing these ripples, Planck scientists extracted a single number, the present-day expansion rate of the cosmos. This number is called the Hubble constant. Planck's final result, published in 2018 and confirmed in 2020, is 67.4 kilometers per second per megaparsec, with an uncertainty of just half a kilometer per second. In plain terms, for every 3.26 million light-years you travel outward, galaxies appear to move away 67 kilometers per second faster. This is not a direct measurement. It is an inference, built from the physics of the universe when it was only 380,000 years old. The method treats the sound horizon, the maximum distance a sound wave could travel in the early universe, as a cosmic ruler. The pattern of peaks and troughs in the background light tells you how big that ruler was. From there, you can calculate how quickly space must be stretching today, if the standard model of cosmology is correct. For a decade, this number, 67.4, has served as the baseline, the slow expansion, the long cosmic timeline, the age of the universe itself. Everything in modern cosmology is calibrated to this ruler. If you accept this value, the entire history of the universe unfolds with mathematical precision. But this is only one side of the contradiction. The late universe approach begins with a different ruler. Astronomers select nearby Cepheid variable stars, pulsing beacons whose brightness cycles with clockwork regularity. By comparing the true brightness to their appearance from Earth, you get distance. These Cepheids anchor the first rung of a cosmic ladder. The next rung is Type Ia supernovae. Each one explodes with nearly identical luminosity, visible across hundreds of millions of light-years. By calibrating supernova distances with Cepheids, the Riess team traced the expansion of space itself, step by step, from the local universe outward. The final number, H0, is 73.2 kilometers per second per megaparsec, plus or minus 0.8. This is not a minor disagreement. It is an 8.6% gap, a chasm, not a crack. If you accept this value, the universe is expanding faster than the standard model allows. James Webb Space Telescope data, released in 2024, sharpened every rung of the ladder. Its infrared vision cut through cosmic dust, eliminating the bias that haunted earlier measurements. Statistical noise dropped by half, yet the answer did not move. The Riess result stands. Cepheids, supernovae, and now Webb all point to the same fast expansion. You live in a cosmos where the numbers refuse to meet. The slow universe of Planck and the fast universe of Riess cannot both be true. The contradiction is now precise, quantified, and undeniable. The numbers are clear. The Planck satellite's early universe measurement, 67.4 kilometers per second per megaparsec, stands against the Riess team's late universe value of 73.2. The gap is 5.8, not a rounding error, not a calibration slip. When you combine the uncertainties, the difference climbs to 6.2 sigma. In scientific terms, that's not a disagreement. It's a statistical wall, a level of certainty so high it would take 1 million coin tosses to reach by chance. This is not a matter of taste or preference. It is a contradiction. The universe cannot expand at 2 rates at once. The age of the cosmos, once thought to be 13.8 billion years, now drops by more than 1 billion years if the higher value is true. Stars and galaxies are squeezed into a shorter timeline. Nobel laureate David Gross called it what it is, a crisis for cosmology. You are living in a universe where the math no longer adds up. Early dark energy, a proposal, not a discovery. The idea is simple. Inject a brief pulse of energy into the universe just before matter and radiation balanced out, at a redshift around 4,000. For a moment, this energy makes up about 5% of everything, enough to speed up the early expansion, enough to shrink the sound horizon by the right amount. The result, when you run the math, is that the Planck satellite's slow expansion rate climbs. The numbers move closer to what you measure from supernovae and Cepheids. Hubble's constant rises to 71. The gap narrows. Not erased, but narrowed. The mechanism is a scalar field, a kind of energy that appears, peaks, and then fades away. By the time the first atoms form, it is gone. The universe returns to its familiar path. No known particle fills this role. No signal of early dark energy has been found in the cosmic microwave background, in galaxy surveys, or in the light from the first stars. Observations from the Atacama Cosmology Telescope and the South Pole Telescope set strict limits. The allowed window is narrow, a few percent for a few thousand years. Anything more would leave fingerprints that have not been seen. You live at a moment when the only theory that fits the numbers is one that remains invisible. Early dark energy is not confirmed. It is the last patch before the unknown. Planck measured 67.4. Riess measured 73. The gap is 8%, more than 1 billion years in the age of the universe. The James Webb Space Telescope confirms it. David Gross calls this a crisis. The Vera C. Rubin Observatory will decide. Subscribe for weekly space documentaries that go deeper.